Imagine opening your terminal, typing a short string of characters, hitting enter, and instantly deleting your entire computer's operating system.
Right, while it is still actively running.
Yeah, exactly. Every file, every driver, every application, just gone in milliseconds. And the machine doesn't even throw a warning pop-up to ask if you're sure.
Not a single warning.
In a Windows environment, that scenario is, practically impossible. The system protects itself from you. It throws up access denied errors. It locks system files. Basically, it treats you like a liability.
It does. It wraps everything in bubble wrap. But in the Linux environment, a catastrophic command like that as well, it's just another Tuesday.
Just another Tuesday. And that is exactly what we are dissecting today. Welcome to a brand new deep dive.
Glad to be here.
If you are tuning in, you're likely preparing for a CompTIA A+ certification or gearing up for a technical role. Or maybe you've just realized that the internet's entire backbone runs on an operating system that absolutely refuses to hold your hand.
Yeah, it assumes that if you typed it, you meant it.
Yeah.
The operating system, it operates on this philosophy of absolute obedience, which is, it's a double-edged sword.
Right.
It never second-guesses your intent, which means it affords you limitless power, but zero training wheels.
Zero. Okay, let's unpack this. Today, our mission is to dive into the CompTIA A+ Model 17 framework. We're looking at the Linux client and desktop operating system. But we aren't just going to sit here and read a list of commands at you.
No, that would be incredibly boring.
We want to decode the architecture. Why is it built this way? What is actually happening under the hood when you hit enter?
Because once you understand the mechanical logic, the raw physics of how Linux addresses hardware and processes data streams, that intimidating black screen with the blinking cursor, it stops looking like a void.
It totally changes.
It does. It becomes an incredibly precise engineering toolkit.
Yeah.
It is, it's the difference between knowing how to drive a car and knowing how to build the engine from scratch.
I love that analogy. Let's start right at the ignition then.
Yeah.
Because the architectural differences between a guided tour OS like Windows and a mechanics OS like Linux start the exact millisecond you press the physical power button on your machine.
Literally the first clock cycle.
Right. We need to talk about bootloaders. The system has to wake up.
The boot sequence is fascinating because the hardware itself, so your motherboard, your CPU, has no concept of what an operating system even is.
Right. It's just dead silicon.
Exactly. When power hits the motherboard, it runs through basic hardware checks, but it needs a bridge to hand off control to the software. And that bridge is the bootloader.
Okay.
In the Linux ecosystem, you are almost always dealing with GRUB, which is the Grand Unified Bootloader, or, occasionally its predecessor, LILO.
Okay, I want to push back on this bridge analogy for a second.
Okay.
Because Windows has a boot manager too. It hands off the hardware to the software just fine. So why do the CompTIA materials specifically highlight GRUB as a distinct defining feature of the Linux environment? Like, what is it doing that the Windows boot manager isn't?
Well, it comes down to flexibility and transparency. The Windows Boot Manager is designed to be invisible.
Right, you never see it.
Microsoft's goal is to get you to the desktop as fast as humanly possible, completely hiding the internal wiring. GRUB, on the other hand, is built to be a configurable management tool before the operating system even exists in memory.
Oh, wow.
Yeah, it natively supports multi-boot environments right out of the box.
So if I have a single hard drive, I can carve it up, put, say, Ubuntu on one slice, Windows 10 on another, and maybe a specialized penetration testing OS like Kali Linux on a third.
Precisely. And when GRUB initializes, it physically stops the boot process and presents you with an interactive menu.
Right on the screen.
Right there. It reads a configuration file and basically says, I detect 3 completely different operating systems on this block device. Which kernel would you like to load into the RAM today?
That's wild.
Furthermore, it gives you the power to intercept the boot process. You can edit the boot parameters on the fly, right there on the screen, passing specific instructions directly to the Linux kernel before it even wakes up.
Try doing that with a standard Windows boot.
Yeah, good luck.
That implies the user is acting as the system administrator from the very first second. Okay, so we took our Linux partition. GRUB fetches the kernel, the core brain of the OS, loads it into memory, and the system boots.
Exactly.
Now we're staring at a screen, and we need to communicate. This brings us to a massive point of confusion. The terms shell and terminal.
Oh yeah, the classic mix-up.
You hear developers use them interchangeably all the time, but structurally they are entirely separate pieces of software, aren't they?
It is the most common semantic trap for newcomers. They are deeply intertwined, but functionally distinct. The easiest way to isolate them is to think about human communication. The terminal is the sensory organ.
The sensory organ, okay.
Yeah. It is the graphical window, the literal box on your screen that captures your keystrokes and displays the text coming back. It is just an input-output interface.
So it has no brain of its own.
Zero. If
How?
you typed a command into a terminal that wasn't connected to a shell, it would be like typing into a dead keyboard. Nothing happens.
Right.
The shell is the actual command interpreter. It is the program running in the background that takes the raw text strings from the terminal, parses them against its own internal grammar rules, and translates them into system calls that the Linux kernel can execute.
So to translate that for our listeners coming from a Windows environment, the terminal is just the window frame. It's the graphical border. The shell is command prompt or PowerShell itself.
A perfect parallel. That's exactly it. And in Linux, the default shell is almost universally bash.
Born again shell.
Right, which is a nod to its predecessor, the original Bourne shell created by Stephen Bourne. But because Linux is modular, bash isn't your only option. You have Zeesh, which has become the default on macOS and is highly favored for its extensibility. You have the fish shell, the dash shell. You can swap out the brain, interpreting your commands whenever you want.
I want to explore how we interact with that brain, because the documentation splits this into two distinct operational modes.
Interactive and non-interactive.
Yes, interactive and non-interactive shells. And I think that this is where the true architectural power of Linux starts to reveal itself. Let's start with interactive. That is what most people picture, right? Sitting at a keyboard, typing live.
Yes. An interactive shell is a live real-time session. You authenticate with your credentials. The system spins up a shell process tied directly to your terminal, and it presents you with a prompt.
Usually a $sign, right?
Usually, for a standard user, it is a $sign. For a root user, it's a £sign or a hashtag. The shell sits there, completely idle, waiting for you. You type else, hit enter, it lists your files, and then it goes back to waiting. It is a synchronous dialogue.
Like ordering live from a waiter at a restaurant.
Exactly.
But the non-interactive shell is entirely different. It doesn't present a prompt. It doesn't wait for human keystrokes. It is an automated process. Think of it less like a conversation and more like an industrial assembly line.
Or a weekly automated grocery delivery.
Right. You write a script, a text file containing hundreds of commands. You hand that script to a non-interactive shell, and it just executes them sequentially, as fast as the CPU can process them, with zero human intervention.
What's fascinating here is that this assembly line analogy is exactly why Linux dominates the enterprise server market. This is how the modern internet scales.
Because you can't type fast enough.
You literally can't. When a massive tech company deploys 1,000 new servers, they don't have engineers opening 1,000 interactive shells and typing configuration commands.
All right, that would take weeks.
They use non-interactive shells to run provisioning scripts. A server boots up. A non-interactive bash script automatically configures the network interfaces, downloads the necessary software packages, patches the security vulnerabilities, starts the web server daemon, and mounts the databases all entirely in the background.
It is pure automation.
Yeah.
The shell does the work and then quietly terminates itself when the script finishes. There is no user interface required.
None at all.
But let's say we're sitting at our desk using an interactive shell. We want to change the brain we are talking to. We are in bash, but we want to try Zesh. Do we have to reboot the machine?
Not at all. Again, it's that modularity. If you just want to test Zesh for your current session, you simply type Zesh at the prompt and hit enter.
Just the letters ZSH.
Yep. The terminal window stays exactly the same, but the bash shell spawns a Zesh child process. You are now speaking to a completely different interpreter. When you are done, you type exit, that child process terminates, and you are dropped right back into your original bash shell.
And to make that change permanent, so Zesh loads every time you log in, the documentation points us to the chush command change shell. You'd run chush command shush.
Exactly.
And if you ever lose track of what shell you are currently operating in, you can query the environment variables by typing echo shell. Okay, so we're in the shell, we're ready to talk. But we need to understand the grammar. Linux commands follow a very strict architectural standard.
It's a legacy of the PESICLE standard, which governs how Unix-like operating systems should behave. The anatomy of a command is incredibly predictable.
Right.
It always follows a specific syntactical flow. The command followed by the options, followed by the arguments.
Let's pull the example from the CompTIA A sources and break it down mechanically. The command is else a home user.
Okay, let's dissect it. First, you have the command a la ls. This is the executable binary program that the shell is going to run. It stands for list. This is your verb.
Okay, verb. like pli for copy or mv for move.
Right. Next, you have the options, frequently referred to as flags or switches. In our example, A, options modify the default behavior of the command. They are your adverbs.
Adverbs. Got it.
By standard convention, short options use a single dash, like F for all, and long options use a double dash, like all.
Makes sense.
Finally, you have the arguments. Arrays. This is the target. It tells the command what specific data or location it needs to operate on. These are your nouns.
Go verb, adverb, noun. Run the list program, modify it to show everything including hidden files, and execute it against this specific user directory.
That's the literal translation.
But here is where we hit a massive stumbling block for anyone transitioning from a Microsoft environment. Case sensitivity.
Oh, this catches everyone.
Here's where it gets really interesting. If I type L's in lowercase, it works. If I hold Shift and type LS in capital letters, the shell throws a command not found error. Why? Windows doesn't care. If I search for a file called budget with a capital B or a lowercase b, Windows just figures it out. Why is Linux so rigidly pedantic?
It's not pedantry, it's mathematical precision. You have to look at this from the perspective of how data is processed at the kernel level. A computer CPU only understands binary sequences.
Just ones and zeros.
Right. Every character you type is mapped to an ASCII or Unicode binary value. A lowercase a and an uppercase a produce completely different binary strings. To the computer's processor, they are as different as the number 1 and the number 9.
So they aren't two versions of the same letter, they're two fundamentally unique entities.
Exactly. When you ask Windows for a file called budget in lowercase, the Windows file system actively runs extra background routines. It intercepts your request and essentially says, well, the user typed lowercase, but let's run a secondary check for uppercase combinations just in case they were being sloppy.
It's spinning CPU cycles, making assumptions about human intent.
Which introduces ambiguity, and ambiguity is the enemy of a stable server environment. Linux assumes nothing.
It takes you literally.
Completely. It operates under the Unix philosophy that the user knows exactly what they want. If you ask for file.txt with a capital F, the kernel looks for that exact binary sequence. It doesn't waste time checking file.txt with a lowercase f. This allows Linux file systems to be significantly faster and more efficient, but it places the burden of accuracy entirely on the user.
It's the digital mechanic philosophy again. The wrench does exactly what you force it to do. And because commands are treated as these isolated, highly predictable tools, we can start chaining them together. We don't have to run one command, look at the output, and then manually type a second command. We can use pipes.
The pipe, represented by the vertical bore, is arguably the most brilliant conceptual design in Unix architecture.
That's a big statement.
I mean it. To understand why it works, you have to understand that every command in Linux has 3 standard data streams. Standard input where data comes from, standard output where the result goes, and standard error where error messages go.
So normally standard input is your keyboard and standard output is your monitor.
Right. But when you use a pipe, you are literally hijacking those streams. You are taking the standard output of the command on the left, and instead of sending it to the monitor, you pipe it directly into the standard input of the command on the right.
The documentation gives a perfect example. ASTLgrep.txt.
Yes.
If you are in a directory with 10,000 files and you just type L's, your terminal is going to flood with thousands of lines of text. It's unreadable.
It just scrolls past instantly.
Exactly. But if you intercept that output stream with a pipe and feed it into grep, which is a pattern matching tool, you can tell grep to filter for DXT. Now, your monitor only displays the text documents. You built a custom 2-stage data processing pipeline on the fly.
You took 2 simple tools and created a complex behavior. That's the beauty of it. And if you want to string commands together that don't need to share data but just need to run sequentially, you use the semicolon.
Just a standard semicolon.
Yeah. Typing cd, etc. is ls vwd. Tells the shell to change the directory, wait for that to finish, then list the contents, wait for that to finish, and then print the current working directory. 3 separate commands, 1 hit of the enter key.
But inevitably, you are going to forget the syntax. You're going to forget which flag does what. In a graphical environment, you just hover your mouse over a button and a helpful tooltip pops up. In the command line, you are staring at a blank prompt. How do we access the manual?
The documentation is built directly into the operating system. You use the man command, which stands for manual pages.
Okay.
If you type man-ls, the terminal replaces your prompt with a highly structured, comprehensive technical document detailing the name, synopsis, description, and every single available option for that command.
And I will warn our listeners, Man pages can be incredibly dense. They read like engineering spec sheets because, well, that is what they are.
They absolutely are.
If you were in the middle of a troubleshooting crisis and you just need a quick syntax reminder, the source highlights a faster method. You pass the help flag to the command itself.
Right. Almost every standard Linux command is programmed to recognize the help flag. If you type pick help, instead of launching a multi-page manual, the command just prints a quick, condensed cheat sheet directly into your terminal stream. It outlines the most common arguments and then gives you your prompt back.
Super useful. And occasionally you're going to need to actually alter the text inside a configuration file. You can't use man or help for that. And you can't double-click the file to open Microsoft Word. You need a text editor that operates entirely within the terminal interface. The CompTIA outline lists a few, Vim, get it, but it specifically zeroes in on Nano for beginners.
And that is a very deliberate choice by the exam creators. Vim is an incredibly powerful modal text editor, but it is notorious for its steep learning curve.
It's brutal.
It is. If you don't know the specific keystrokes to switch between command mode and insert mode, you literally cannot even figure out how to exit the program. People get trapped in Vim.
I have absolutely had to hard reboot a server in my early days because I got trapped in Vim and panicked.
We've all been there. Nano solves that problem. When you type nanoscript.esh, it takes over the terminal and behaves much more like a standard text editor you are used to. But crucially, it constantly displays a cheat sheet of keyboard shortcuts right at the bottom of the screen.
The sources highlight 3 specific Nano commands that you absolutely must commit to memory. First is Ctrl plus O, the letter O, meaning write out. This is how you save your changes to the file.
Right.
Second is Ctrl plus X, which is how you close Nano and exit back to your shell prompt. And third is Ctrl plus K, which acts as a quick cut command, instantly deleting the entire line of text your cursor is currently resting on.
It provides a necessary bridge for beginners. But we should also clarify that you don't have to live in a text-only terminal forever. Linux has fully featured graphical environments. This is the desktop environment layer.
Right, the graphical escape. If you install Ubuntu or Fedora on a laptop today, it boots into a beautiful mouse-driven interface. You have windows, taskbars, and icons. But architecturally, this is fundamentally different from how Windows handles its GUI, isn't it?
Completely different. In Microsoft Windows, the graphical user interface is deeply intertwined with the operating system kernel. They are fused together. In Linux, the desktop environment, whether it is GNOME, KDE Plasma, or XFCE, it's just another application running on top of the system.
It's an app.
Yeah, it's a client interacting with a display server like X11 or Wayland.
Meaning the Linux OS doesn't actually care if the GUI exists or not.
Exactly. You could uninstall the entire GNOME desktop environment, and the core Linux operating system would continue running perfectly fine in the background.
That's crazy to think about.
This separation of concerns allows for incredible stability, and it also allows for features that Linux perfected decades ago, like workspaces.
Virtual desktops. The ability to hit a keyboard shortcut, use a Strl, Alt, and the arrow keys, and physically slide your entire screen over to a brand new, empty desktop environment. You can have your coding IDE open on Workspace 1, your web browser on Workspace 2, and your server logs on Workspace 3. It organizes your workflow without requiring 4 physical monitors.
And because the GUI is just an application layer, it leads to a brilliant troubleshooting feature called console switching.
Oh, I love this feature.
It's a lifesaver. Linux runs multiple virtual terminals, or TTYs, simultaneously in the background. If you are in your graphical desktop and the entire GUI freezes, your mouse won't move, the windows are locked, you don't have to hold down the power button and crash the machine.
You can just step outside the matrix.
Exactly. You press Stdl, Alt, F3 or F1 through F6 depending on your distribution, the frozen graphical screen instantly vanishes, and you are dropped into a pure black and white text login prompt.
But the OS is still running.
The underlying operating system is still humming along smoothly. You log in via the text shell, you find the process that crashed your GUI, you kill it, and then you press Ctrl Alt F7 to flip back to your graphical session, which will now have refreshed and recovered.
It is the ultimate safety net. Okay, so we understand the commands. We know how to use the text editor. We understand the GUI abstraction. But if we are typing commands, where are they actually executing? We need to map the territory. We need to talk about the Linux file system architecture. And to do that, we have to start at the root.
This requires a total mental reset if you are accustomed to Windows.
Definitely.
In Windows, storage is divided into distinct drive letters. Your operating system lives on the C drive. If you plug in a USB stick, it becomes the D drive. They are separate, isolated plots of land. Linux does not use drive letters. Linux uses a single, unified, hierarchical tree structure called the virtual file system.
Everything grows from one central trunk.
Yeah.
And that trunk is the root directory, represented by a single /.
Every single file, folder, program, and piece of hardware on a Linux machine exists somewhere under that one /. When you expand it, it branches out into standardized directories defined by the file system hierarchy standard. You've been for essential user binaries and commands, etc., for system-wide configuration files, home for user data, var for variable data like system logs, and tm for temporary files.
It's incredibly elegant. No matter how many hard drives you add to a server, they all get grafted onto that single tree. But we need to clarify a massive point of terminology confusion here. The word root.
Yeah.
Because there is the root directory, which we just defined as the top of the file system tree, but there is also the root user.
And conflating the two is a recipe for disaster.
They separate them.
Okay, the root directory, the /, is a location. The root user, often referred to simply as root, is an identity. It is the super user account, historically assigned the user ID of 00. The root user has absolute, unrestricted power over the entire operating system. They can read any file, modify any configuration, and execute any command.
They are the entity with permission to modify the root directory. Okay, so we have our tree. How do we traverse it from the command line? The CompTIA A outline highlights 4 core navigation commands. Let's start with getting our bearings. The PID command.
PID stands for Print Working Directory. In a graphical file explorer, you always have an address bar at the top telling you what folder you are looking at. In a text terminal, you just have a prompt. If you get lost deep in the file system, you type POD.
And it just spits out the path.
The system makes a system call to the kernel and returns your absolute path, starting all the way from the root. It might output home student documents projects. It gives you your exact coordinates on the map.
Where am I, basically?
Right.
Once we know where we are, we need to move. That's CD, change directory. And this is where we have to understand the difference between absolute paths and relative paths.
An absolute path always starts from the root. If you type CD, etc., you are telling the system exactly how to get there from the very top of the tree, regardless of where you currently are.
You're giving it the full GPS coordinates.
Yes. A relative path, though, depends on your current location. If you're already inside Home Student and you type CD documents without the / at the beginning, the shell looks for a folder called Documents immediately inside your current directory.
The outline also specifically highlights 2 essential CD shortcuts. If you are 5 folders deep and you just want to move up one single level, like hitting the up arrow in a GUI, you type CD, that's CANDACD space ...
Right. Those 2 dots are actually a hard link dynamically pointing to the parent directory.
And if you want to instantly teleport back to your own personal user folder, no matter where you are in the entire file system, you type CD, the tilde symbol.
The shell automatically expands that tilde into your specific home path, like home username. It is a brilliant time saver.
So PWD gives us our location. CD moves us. Now we want to look around. We use else, which we touched on briefly. It lists the contents of the directory. But running a plain else just spits out names. It doesn't tell us much about the architecture. We need to use flags to get the real data.
The most critical flag is LL, which stands for long format. When you run LL, it queries the inode of every file.
An inode?
An inode is a data structure in the kernel that stores all the metadata about a file. It returns the file's exact size in bytes, who owns it, what group it belongs to, its permission string, and the timestamp of exactly when it was last modified.
That's a lot of info. And as we discussed earlier, if we want to see hidden files, we add the A flag. But Sunny, in Linux, hiding a file doesn't require checking a special properties box like in Windows.
No, you literally just put a dot at the beginning of the file name.
Just period.
Yeah, a filename.config is automatically invisible to a standard else command.
Which brings us to the 4th navigation command.
Yeah.
You found a text file and you want to read it, but you don't want to open the nanotext editor because you don't want to risk accidentally modifying it. You use cat.
Which does not stand for the animal.
Right, it stands for concatenate.
Cat takes the contents of a file and streams it directly to standard output your terminal screen. If you typed cat at ghost's name, it prints the name of your computer on the next line and gives you your prompt back instantly. It's the fastest way to inspect a small configuration file.
So we can walk around the tree and we can look at files. But what if we don't know where a file is? If you have millions of files on a server, manually using CD and alls is impossible. We need to talk about the hunt. How do we search and manipulate data?
The CompTIA A module outlines two primary search utilities, and they operate on entirely different mechanical principles. The first is find.
Okay.
The find command traverses the directory tree in real time, looking for files based on their metadata, so their name, their size, when they were created, or who owns them.
The syntax looks like this. Find varlog-name.log. Let's break that down. Find is the verb. Varlog is the starting directory. It tells the command where to begin searching. Name is the option, telling it to search based on the file's title. And .log is the argument, telling it what to look for.
Notice the asterisk in that argument. That is a meta character, commonly known as a wildcard. The shell expands that asterisk to mean match absolutely any string of characters. So it will find syslog.log, auth.log, error.log.
Any of them.
Right. Another common wildcard is the question mark, which forces a match on one and only one single character.
But this introduces a mechanical problem. What if a file literally has an asterisk in its name? What if a poorly written script generated a file called data.txt? If you type find.nameData, the shell is going to intercept that asterisk and try to run it as a wildcard before the find command even sees it. It'll break the search.
Which is why we have the concept of escaping. You have to tell the shell to turn off its special processing for that specific character. You do this by placing a backslash immediately before the meta character.
So backslash asterisk.
Right. By typing data, you escape the asterisk. The shell sees the backslash and says, okay, pass the very next character to the command as raw text.
It strips the magic away from the wildcard. Now, find is brilliant for locating the container of the file itself. But what if I need to search the contents? What if I am trying to troubleshoot a crashed web server and I need to comb through a massive text log to find the specific line where the word timeout appears? Find can't look inside files.
For that, you use grep, Global Regular Expression Print. Grep is a text parsing engine. It reads the standard input stream line by line, scans it for a specific text pattern, and only outputs the lines that match. You would type grep timeout varlog-2error.log. It ignores the thousands of lines of normal traffic and only spits out the specific error lines to your screen.
And because it operates on data streams, grep is constantly paired with pipes. You can run a command that outputs massive amounts of diagnostic data, pipe it into grep, and instantly filter out the noise. It is a surgical tool.
It really is.
But once we find the files, we have to manage them.
Right.
Let's look at the three core manipulation commands: CP, MV, and RM.
Copy, move, and remove.
Yep.
CP is straightforward. You provide a source and a destination. CP, home user document.txt mnt backup.
Simple enough.
If you are trying to copy an entire directory full of files, you must include the asr flag for recursive. This tells the command to dive into the folder, copy its contents, find any subfolders, dive into them, and repeat the process until it hits the bottom.
Then we have MV, which stands for move.mv document.txt mnt backup. It removes the file from the current location and places it in the new one. But MV handles a second incredibly important function in Linux. It is how you rename files.
Which conceptually makes perfect sense if you understand inodes.
Right, the metadata tags we talked about.
Exactly. An inode points to physical blocks of data on the hard drive. The file name is just a human-readable label pointing to that inode. When you type mv oldname.txt, newname.txt, you aren't actually moving the physical binary data on the disk.
You're just changing the sign on the door.
Precisely. The mv command simply updates the directory registry to point the new name at the exact same inode. This is why renaming a massive 50-gigabyte video file happens instantly in Linux. The data doesn't move, only the label changes.
That is a phenomenal aha moment for understanding how the system actually works. But this brings us to RARM remove. And this is where we have to have a serious conversation about the lack of a safety net. In Windows, if I highlight a file and hit delete, it doesn't actually delete it. It moves it to a hidden folder called the recycle bin. I can go in there 3 weeks later and restore it. How does RARM work under the hood?
There is no recycle bin in the standard Linux command line environment. None.
None at all.
When you execute the RARM command, it issues an unlinked system call to the kernel. It immediately severs the connection between the file name and the inode and marks those data blocks on the hard drive as unallocated and available to be overwritten.
So if I hit enter, it is gone forever.
Instantly.
So what does this all mean for someone with butterfingers? Once I hit enter, is it really gone forever?
It raises an important question about safety versus efficiency. Why is it designed this way? Think back to our non-interactive shell discussion. If a massive server is running automated scripts that create and delete thousands of temporary cache files a minute, and those files went into a recycle bin, the server's hard drive would fill up and crash the system in an hour.
Right, it would choke on its own trash.
Exactly. The system is designed for high-performance automation. It assumes the user knows exactly what they are doing.
There was a famous story about the production of the Pixar movie Toy Story 2.
Oh, I know this one.
An animator accidentally ran ARM, ARE at the root level of the project drive. The ARM meant recursive, and the asterisk was the wildcard, meaning everything. They literally watched the movie files deleting themselves in real time on their terminal screen. The entire film was almost lost because ARM does not ask for confirmation.
It is a terrifying reality of the system, which is why the CompTIA A outline stresses the I flag. If you type rmfsha file.txt, the I size stands for interactive. It forces the command to pause and prompt you. Remove regular file.txt. You have to explicitly type Y for yes. It is the one time the system will double-check your math.
Conversely, you have the F flag for force.rm-rf tells the system, recursively delete everything in this path and ignore all warnings, all read-only locks, and do not prompt me. It is the most dangerous command in the entire operating system. You should treat the F flag like a loaded weapon.
And a final best practice when managing files. If you are going to use LM with a wildcard, always test it with else first.
Oh, that's smart.
If you want to delete all text files and plan to type rm.txt, stop. First, type ls.txt. Hit enter. Look at the exact list of files the shell expands that wildcard into. Verify with your own eyes. Only after you confirm the list is correct should you press the up arrow, swap the L's for R, and execute the deletion.
Measure twice. Cut once. Okay, so we are manipulating files, we are copying them and destroying them. But where do these files physically live? The files exist on hardware on SSDs and USB drives. This brings us to section 5 of our journey, making space. How does Linux physically mount and address block storage devices?
Well, we established earlier that the Linux file system is a single unified tree starting at the root. But a physical hard drive is an external piece of hardware. When you plug a USB drive into a Windows machine, the plug-and-play service intercepts it, formats GUI pop-up, and assigns it an entirely new drive letter, like E. It creates a new plot of LAN.
But Linux doesn't do drive letters. So instead of getting a new E drive, mounting a USB in Linux is like grafting a new branch directly onto your existing tree at a specific knot.
Right. Exactly right. It's a process called mounting. You have to take the raw block device, the physical hardware, and logically attach it to a specific empty directory on your existing tree. That empty folder is called the mount point.
Let's walk through the mechanics of the mount command provided in the sources. sudo mount devs db1 mn2sp. Let's translate this. Mount is the command. Devs db1 is the source. The dev directory is fascinating because it is where Linux creates special files that act as direct interfaces to your hardware. SDB1 means SESI disk B, partition 1. That is the actual physical USB drive plugged into the motherboard. And M2s is the destination. It is just an empty folder we created on our root tree specifically for this purpose.
Perfectly stated. When you execute that command, the virtual file system intercepts any requests made to M2s and seamlessly redirects them to the physical USB drive. You aren't going to a separate drive, you're just walking into a folder.
And when you're done.
When you're finished, you must sever that logical connection before unplugging the drive using sudo amount mpsb. Notice the spelling. It is mount, U-M-O-U-N-T, not unmount.
Doing this manually is fine for a flash drive. But what about the internal hard drives inside a server? We don't want to log in and manually type mount commands every time a server reboots just to attach the database drives. How does the kernel know how to rebuild the tree automatically?
It relies on a critical configuration file located at etc. stab, which stands for File System Table. This is a plain text blueprint. During the boot sequence, the init system reads this file line by line to determine exactly which hard drives to mount, where to mount them, and what rules to apply to them.
In a Windows environment, this auto-mount logic is buried deep inside the Windows registry or disk management snap-ins. It is hidden behind GUIs. In Linux, it is literally just a text file. If you open etc. stab and nano, you can completely reconfigure the storage architecture of the machine. The outline breaks this file down into 6 distinct columns. We need to explain what each column is doing.
Right. Each line in the fafstab file represents one partition, and the columns read from left to right. Column 1 is the device. Historically, this was the devs.1 path. But today, we use UUID's universally unique identifiers. This is a massive string of alphanumeric characters hard-coded into the partition.
Why the switch to UEDs?
Because hardware paths can change. If you unplug a drive and plug it into a different SATA port on the motherboard, what used to be SATA might suddenly become SDB. If STAT was looking for SATA, the server would fail to boot. A UUID never changes, regardless of which port the drive is plugged into. It makes the boot process bulletproof.
That makes total sense. Okay, column 2 is the mount point. Where on the tree is this drive going? Usually to, or home, or var. Column 3 is the file system type. This tells the kernel how the data is formatted. Is it a modern journaling file system like X4 or XS? Or is it a Windows NTSS drive? The kernel needs to know which driver to load.
Then column 4 holds the options. These are specific parameters for the mount. You will often just see defaults, which grants standard read-write access. But for a highly secure server, you might see row for read-only or no exec, which physically prevents any binary file on that drive from being executed as a program, severely limiting malware risks.
Oh, that's granular.
It is. Column 5 is the dump flag. This is a legacy setting used by old Unix backup programs. In modern systems, it is almost universally set to 0, meaning ignore. And column 6 is the SICK pass number. This tells the system in what order it should check the disks for physical errors during boot. The root file system is always 1. Secondary drives are 2. If you don't want the drive checked at boot, you set it to 0.
It is incredibly powerful, but because it's just a plain text file rather than a hidden registry setting, it makes the system totally transparent to the user. But it's also completely unforgiving. If you miss a space or type a UUID incorrectly and then you reboot the server, the kernel will read the broken fstab file, panic, and drop you into an emergency recovery shell. How do we test our changes safely before rebooting?
The source highlights the sudo mount a command. The coroutine flag tells the mount utility to parse the etc fstab file and attempt to mount everything listed in it immediately.
So you run it live?
Right. If you made a syntax error, it will throw a loud error right there in your terminal while you are still safely logged in and can open Nano to fix it. Never reboot a server after editing stab without running mount F first.
You mentioned the SICK pass number earlier.
Yeah.
SPIC stands for File System Check. This is the Linux equivalent of the Chica disk utility in Windows. If a server loses power unexpectedly, the file system can become corrupted. You run sudo stick devzel1 to scan the raw block device, repair broken inodes, and recover orphan files into a lost plus found directory.
Exactly. And while Fix checks the health of the drive, you also need to monitor the capacity of the drive. A full hard drive will crash a Linux system just as fast as a corrupted one. The outline provides 2 specific commands for auditing space, df and do, and they're constantly confused by beginners because their algorithms operate fundamentally differently.
Let's clarify them. df stands for disk free.
df queries the file system's superblock. The superblock is a master record that keeps track of the total number of blocks on the physical partition and how many are currently unallocated. When you run df, it is a near instantaneous query. It simply looks at the master ledger and reports, this partition has 100 gigabytes total and 20 gigabytes are free.
It doesn't care what files are taking up the space. It is just looking at the gas gauge on the dashboard. And the source specifically notes using the H flag, DFH. That stands for human readable. Instead of outputting the size in a massive unreadable string of 1K blocks, it converts the output into megabytes and gigabytes.
Right, but if DF tells you that your home partition is 99% full, it doesn't help you find the culprit. That is where you use do, which stands for disk usage. Do does not look at the master ledger. Do actually traverses the directory tree.
It crawls the files.
Yes, it walks into a folder, looks at every single file, calculates the size, walks into the subfolders, and tallies everything up.
So it is an active scanning algorithm. If you run do-dash home your downloads, the d-dash means summarize, and the hh means human readable. It will crawl through your downloads, add up all the ISO files and zip archives, and output a single line, 50 gigabytes. It tells you exactly who is eating all the space.
df gives you the macro view of the partition. Do gives you the micro view of the directory structure.
Okay, we have built a perfectly organized, searchable file system. We have successfully mounted our hard drives, we are monitoring their health, and we are managing our capacity. But we are acting as if we are the only person on this computer. Linux was fundamentally designed from day one to be a multi-user operating system. We need to talk about Section 6, the bouncers. Users, groups, and permissions.
You have to remember the historical context. Unix and Linux were born in the era of mainframes. You had one massive room-sized computer in the basement of a university and 50 students simultaneously connecting to it via dumb terminals.
A completely shared environment.
The entire architecture of the operating system had to be built around strict isolation. User A cannot be allowed to read user B's files, and neither of them can be allowed to accidentally delete the kernel.
Security isn't bolted onto Linux. It is baked right into the subatomic layer of the file system. Let's start with basic user management. When I log into a machine, I am authenticated as my specific user account, but sometimes I need to run commands as a different user, maybe a service account designed to run a database. How do I switch my identity?
The historical command is su, which stands for substitute user. If you type su database admin, the terminal prompts you for that user's password. If you authenticate successfully, your shell spawns a new session. You are now entirely operating under the permissions and identity of that other user. When you are finished, you type exit to terminate that session and return to your original account.
But this brings us back to the most dangerous user on the system, the root user. If I need to install software with the app package manager, or if I need to edit the etc.res.stab file we just talked about, standard users are denied access. I need root privileges. So should I just type su root?
You can, but in modern enterprise environments, it is considered a severe security violation. If you run su root, you escalate to the superuser indefinitely. Your prompt changes to a hashtag, and you are God.
And what's the problem with that?
The problem is twofold. First, humans are forgetful. You might fix the FastStab file, forget you were still logged in as root an hour later, and then accidentally run an ARM command that destroys the server.
The blast radius is too large.
Exactly. The second problem is auditing. If 5 different administrators all use su root to log into the superuser account and someone accidentally deletes a database, the system logs only show that root did it. You have no idea which physical human being was behind the keyboard.
And this is why the sudo command was invented. Superuser do.
Sudo is a paradigm shift in security. Instead of permanently changing your identity to root, sudo allows you to execute one single specific command with escalated privileges and then instantly drops you back to your normal user state.
That's brilliant.
You type sudo nano etc.stab. The system pauses and asks for your password, not the root password.
Because it is authenticating that you are who you say you are, and then checking a special configuration file, the sudoers file, to see if your specific user account is authorized to borrow root powers.
Precisely. The privilege escalation lasts for the exact millisecond it takes to launch Nano. Once Nano closes, you are a normal user again. And critically, the system logs note exactly who ran the command. User Alice executed Nano as root. It creates a perfect, auditable paper trail while minimizing the blast radius of human error.
Managing the actual user accounts relies on very literal commands. Username provisions a new account. Userdel, username removes them. And password username changes their password credential. But managing permissions for 50 individual users is an administrative nightmare. You don't assign rights to individuals, you assign them to groups.
Groups are the fundamental mechanism for managing shared resources. If you have an accounting directory, you don't write a script to give Bob, Susan, and Dave individual access. You create a group called accounting. You use the user mod's ag accounting Bob command to append Bob to the group. Then you assign the directory permissions to the group itself.
So if Bob transfers to a different department, you just remove him from the group and his access is instantly revoked.
Right, much cleaner.
And just like the stab file for hardware, this user data isn't hidden in a registry. It is stored in plain text files. The etc. password file lists every user and their corresponding user ID number. The etc. group file lists every group. You can read them with the cat command.
Which brings us to the absolute core of Linux security. How do these users and groups actually interact with the files? This is defined by file permissions. When we discussed the else all command earlier, we mentioned it outputs a permission string.
Yes, the symbolic notation. And for a beginner, this is the most intimidating part of the command line. You run rlr, and on the far left side of the screen, you see a string of 10 characters that looks like a cat walked across the keyboard. Net rw xr and wrr.
It does look like gibberish.
It looks like an alien language. We need a simple mental model to decode this on the fly.
It looks chaotic, but it is actually a highly structured matrix. The secret is knowing exactly where to slice it. You start by ignoring the very first character. That single character just defines the file type. A dash means it is a regular text file or binary. A letter D means it is a directory.
Okay, so we slice off the first character. We are left with exactly 9 characters.
Right. Do not try to read those 9 characters as a single word. You must read them strictly in blocks of 3. The first block of 3 defines the permissions for the owner of the file. The second block of 3 defines the permissions for the group assigned to the file. The third block of 3 defines the permissions for others, meaning the rest of the world. Any user on the system who is not the owner and not in the group.
Owner, group, others, U, G, O. That defines the who.
Correct. Now, inside each of those blocks of 3, you have the what, the actual rights. And they're hard-coded to always appear in the exact same sequence. Read, write, execute, .rwx.
Let me guess. .r means read. Can the user look at the contents of the file?
Exactly. W means write. Can the user modify or delete the file? And X means execute. If the file is a script or a compiled binary program, is the user allowed to run it?
So let's apply that matrix to the example string from the outline. -rwxrwx, we drop the first dash. It is a standard file. Block 1, the owner.rwx, read, write, execute. The owner has absolute full control. They can read it, edit it, and run it. Spot. Block 2, the group.rw, read, write, dash. The group can read it and edit it, but the dash means the execute bit is turned off. They cannot run it as a program.
Yep.
Block 3, others.rw, read, dash, dash. The rest of the world can only read the file. They cannot edit it, and they cannot run it. When you slice it into 3 blocks of 3, the alien language instantly translates into a clear, logical security policy.
It's brilliant in its simplicity. But what if you are the owner and you need to change that policy? You use the chan command, which stands for change mul. The source highlights a specific way to do this using octal numeric notation, like chan 755 script.
And this is where the math comes in. Where does the number 755 come from? It corresponds directly to our blocks of 3, right?
Exactly. It's binary math. In the computer's memory, those R, W, and X values are just switches. 1 for on, 0 for off. The read bit is assigned a value of 4. The write bit is assigned a value of 2. The execute bit is assigned a value of 1.
So if you want full permissions read, which is 4, write, which is 2, and execute, which is 1, you add them together. 4 plus 2 plus 1 equals 7.
Correct. If you want read and execute but no write permissions, you add reads 4 and executes 1 to get 5. So when you execute the command chmod 755script.esh, you are assigning a 7 to the owner rwxa, to the group rx, and a 5 to others rx.
You are explicitly declaring, I am the owner, I can do whatever I want. Everyone else on the system can read this script and run it, but they are physically barred by the kernel from altering the code inside it.
And the outline provides a second example. Crotch 770 project folder. This assigns a 7 to the owner, a 7 to the group, and a 0 to others.
And 0 means 0 access.
Absolute 0. If a user who is not the owner and not in the group even tries to run the cd command to look inside that folder, the kernel intercepts the system call and throws an access denied error.
The system assumes nothing.
Yeah.
It explicitly requires you to define every single vector of access. If you need to physically hand the file over to a different user, you use the final command in our module.chown, change ownership. Sudo chown userfile.txt permanently alters the inode metadata, making the new user the absolute owner of the file.
What is truly remarkable about Shuman and Chown is how they represent the ultimate philosophy of Linux security. Granular, explicit control where the system assumes nothing and requires you to define exactly who is allowed through the door. If you have ever tried to troubleshoot file permissions in a Windows Active Directory environment, it can be a nightmare.
Well, don't get me started.
You have explicit permissions, inherited permissions from parent folders, deny rules taking precedence over allow rules, security groups nested inside other security groups. You often need specialized software just to figure out why a user can't open a PDF.
It's a black box.
In Linux, there is no black box. You run lzil, you look at the owner, you look at the group, and you read the 9-character string. The entire security posture of the file is rendered in plain text right there on your screen. If a user cannot execute a script, it is because the X bit is a dash, period. You used shimid to flip the bit, and the problem is solved. It is absolute, unyielding transparency.
It demands that you understand the machinery, but once you do, you have total control. Let's take a breath and zoom out, because we have covered a massive amount of architectural ground today.
We really have.
We started at the literal power-on sequence, bypassing the hidden Windows boot manager to use GRUV, intercepting the kernel before the OS even loaded.
We established the critical difference between the terminal as a sensory interface and the shell as the actual processing brain. We explored how interactive shells facilitate our dialogue, while non-interactive shells power the automated backbone of the modern internet.
We decoded the strict PO60's grammar of commands, the verbs, options, and arguments. We learned why case sensitivity isn't Linux being stubborn, but a reflection of raw binary truth. We hijacked data streams using pipes to build complex processing lines, and we established our graphical abstraction layer with X11 and Wayland, proving the GUI is just an app you can kill and restart via virtual TTY console.
We completely mapped the virtual file system, abandoning Windows drive letters to understand the single unified tree growing from the root directory. We learned how inodes allow instant renaming with MV, and why the preserm command's direct unlinking procedure makes the lack of a recycle bin a necessary feature for high-performance servers, not a bug.
We logically grafted hardware onto our file tree using the mount command and hard-coded the acetostab blueprint with UUIDs to survive reboots. We monitored our capacity using the master superblock with DF and actively crawled our directories with do.
And finally, we locked the entire architecture down, tracing the mainframe heritage of Unix timesharing to understand why the root user must be guarded by sudo, and how the binary math of chwad provides a granular, perfectly transparent security model.
We didn't just read you a list of commands for your CompTIA A+ exam. We decoded the philosophy of the operating system. Linux is not a consumer appliance. It is not designed to hide the wiring or protect you from your own mistakes. It is a modular, highly transparent toolkit designed to grant you absolute, granular power over the silicon.
If you are willing to speak its language with precision, it will do exactly what you tell it to do, at speeds and scales that GUI-based systems simply cannot match.
And that leads me to a final thought I want you, the listener, to mull over as we wrap up this deep dive. The entire computing industry is currently accelerating toward abstraction. We live in a world of locked-down, walled garden devices.
Totally.
When you use your smartphone or your tablet or even a modern Mac, the file system is hidden from you. You can't see the root directory. You can't access a terminal. You are restricted to touching shiny icons and operating strictly within the parameters that the manufacturer deemed safe.
They trade your control for your convenience.
Exactly. The complexity is hidden, and therefore the ownership is leased. So here's my question for you to explore on your own. In a technological landscape that is aggressively trying to turn you into a passive consumer of software, is learning the Linux command line fundamentally an act of reclaiming ownership? When you understand the binary math of a chmod string, when you can manually graft a hard drive onto a virtual file system using a text file, does that make you one of the last true digital mechanics in an era of sealed engines?
It's a critical perspective. Understanding the terminal means you aren't reliant on a developer building a button for you. You have the raw materials to build the button yourself.
And that architectural understanding is a skill set that will outlast any specific graphical interface or trendy app. We highly encourage you to spin up a virtual machine, open a bash shell, and try running these system calls for yourself. Delete a test file with Warm, edit a configuration with Nano, experience that unmediated control. Thank you for joining us on this deep dive into the underlying architecture of the Linux client. Remember, the guided tour might be comfortable, but holding the reins yourself. That's where the real power is. Until next time.